Welcome back. The second component that we're going to look under the topic of intermolecular forces is hydrogen bonding. Okay, now hydrogen bonding is probably one of the most unique and most common and probably the most influential type of bonding that you can find. Okay, why is that so important? Okay, water. Okay, H2O. Okay, if you all remember when we had our VSEPR lecture in 170, you probably all remember that you developed something like this, drew something like this. Okay, now the lone pair itself is not influential in the hydrogen bonding process. Okay, it's the oxygen and the hydrogen itself that contributes to the hydrogen bonding. All right, now let's look at what type of elements can actually hydrogen bond. Okay, well, obviously they all must have hydrogen as a component, but here's the thing. Okay, so if your compound contains nitrogen which is directly attached to hydrogen, now this could be attached to anything else, all right, but the hydrogen must be directly attached to the nitrogen. The second is oxygen, which is attached to a hydrogen, and this could be attached to anything else. Similarly, if your compound contains fluorine, and the hydrogen must be attached to the fluorine directly. Now keep in mind, what you have to really focus on here is just because a molecule contains nitrogen, oxygen, or carbon, or hydrogen does not automatically make it a candidate for hydrogen bonding. Okay, the molecule must contain nitrogen and hydrogen, and the hydrogen must be directly attached to the nitrogen like it's shown here. Okay, you see it? The hydrogen is directly attached to these three elements, and this is the only combination that can result in hydrogen bonding. For instance, let's say I have acetone, which is commonly used in lipsticks and nail polish and stuff like that, right? Now, does this compound contain oxygen and a hydrogen? You sure bet. But is the hydrogen attached directly to the oxygen? No. So this compound is not eligible for hydrogen bonding. And if you remember, when I talked about boiling points, I talked about acetone. Okay, acetone is highly volatile. Okay, this is volatile, means it has high vapor pressure and low boiling point, means it boils very quickly. Okay, now why is that the case? That is simply because of the fact that this compound lacks hydrogen bonding. Now, say if acetone boils at say 50 degrees Celsius, don't quote me on it, that's probably not the true temperature, but say it's 50 for this temperature, for this compound right here, we already know water boils at 100 degrees. That's takes twice longer at least for water to boil. Why is that the case? Because in water, the hydrogen is directly, you see, it's directly attached to the oxygen. Right? Hydrofluoric acid, which is a very, very strong acid. It's used in etching glassware. And the reason it can etch glass is because of the fact that the hydrogen and fluorine can hydrogen bond with the glass, the surface of the glass easily. And water, I've already talked about. Many of your proteins and amino acids, they all contain nitrogen-hydrogen bonds, which is why several of the amino acids are soluble in water, right? And which is why they're soluble in blood as well, right? So this is the criteria. What is the criteria again? The hydrogen must be attached directly to only these three elements. Only these three elements, when they are directly attached to hydrogen, can result in hydrogen bonding. Okay, just because the compound contains oxygen or hydrogen somewhere in the molecule does not automatically lend itself to hydrogen bonding, right? Now, let's say we have a compound, say glycerol, okay? So, okay, okay, or yeah, this is glycerol, okay? This is an important concept that we will come back to when we um, talk about viscosity. Okay. Now let's say if we compare this to water, okay, which is looking like this, which one of the two would have higher hydrogen bonding? Well, water only has two sides, which is this or this, right? Whereas glycerol has 1, 2, and 3. So glycerol has higher um, opportunities for hydrogen bonding over water, which means glycerol even boils at a higher temperature than water, right? So if water boils at 100, I'm just making this number, glycerol could boil at 150 degrees Celsius. Why? Because of that extra hydrogen bonding, right? So only the conceptual questions I might test you on this particular concept has to do with, I could give you a bunch of molecules and have you either identify which ones actually can result in hydrogen bonding, or once you've identified which ones have hydrogen bonding, you have to sort them in from, say, low boiling point to high boiling point, right? And how do we determine that? Based on typically among these three, okay, compounds containing nitrogen, hydrogen is slightly less boiling point than compound containing oxygen, hydrogen, and then one's containing hydrogen fluorine has. So if a compound contains nitrogen, hydrogen type of bonding, it will have the lowest boiling point. Among these three, this will have the highest boiling point. Okay, right. So most of the questions on this particular topic of intermolecular forces would be conceptual. In other words, you don't necessarily have to do some math problems to prove to me that you understand this concept, right? I got one more quick thing to share with you, and that will be part of the second video on this concept of hydrogen bonding. So stay tuned for that.